So I put the YouTube live as well, and then I think we can start. Okay, I think Andy, maybe we start. What do you think?
Sure. Yep. Have you launched all the recordings, Oriel?
Yes,
Okay.
Everything is recorded and on live on YouTube. We are 27 participants, so it's good.
Excellent. Well,
people will connect, I hope.
Let's begin. Welcome back, everyone. We've given Arlene a well-deserved rest from her eruption monitoring and presentation and organization duties. She's done far too much already. So I'll step in and do the convening this afternoon, and she can sit back, close her eyes, go to sleep and rest. Thanks, Arlene. Thanks loads. So this morning we saw from Matthew, for example, the high temporal resolution monitoring from satellites that's targeted at Piton de la Fournaise for crisis response and providing data sets for unrest. And we also began to explore and see how hazard maps are created in real time and handed on to civil protection. This afternoon, we're going to continue on that line with looking at other means of remote sensing monitoring of effusive crisis with a focus on Piton de la Fournaise. That'll begin with Diego, who will present Morova and what Morova does and how it does it. And then Mike Ramsey will be talking about ASTA monitoring and the urgent response protocol. And then we'll finish with Pierre and Oriel to talk about the modeling capabilities and the detail as to how the models can be used and are used to create the hazard maps. So without any further delay, let me hand over to Diego. Diego,
Andy?
Hello?
Yeah, Andy, quickly, also at the end, we'll have Caroline Greza.
Okay, I was wondering if we were going to have a pause before Caroline.
We can,
okay.
Actually,
so,
but maybe...
So at the end of the afternoon, we're going to change direction a bit and begin the society issues. And we've got Caroline Reza, who's a specialist in social media communication during crises. And she's going to talk to us and give us a few case studies on how social media can be used to help in a crisis, or on the other hand, help make the crisis worse. There are three examples from beyond volcanological crises, the meteorological crises and terrorist crises. But the message crosses over nicely to any type of crisis, whether it's geological, volcanic, or meteorological. So that'll be our final presentation of the afternoon, and then we'll open the floor to some final discussion. So now, Diego, it's definitely you. Over to you. You're free to share the screen.
Okay, thank you very much, Andy. Okay, can you see my screen?
You're good.
Okay. So thank you, Andy, and thank you to all the organizers for inviting me in this workshop. And I will talk in this presentation on the estimation of effusion rate data from in particular from MODIS and from the Mirova system. So the talk is subdivided in 4 parts, and I will give an overview of Mirova, and then I will enter more in detail on the estimation of effusion rate and the delivery of this data to the observatories. So MIROVA stands for Middle Infrared Observation of Volcanic Activity. It's a project which born some years ago in collaboration with the University of Florence and the group of Maurizio Di Pepe, and was specifically designed to monitor Etna and Stromboli from space, in particular the thermal emission of these volcanoes. Now it's extended to more than 200 volcanoes all around the world. MIROVA is based on the analysis of MODIS data, and MODIS is a spectroradiometer which is carried on two NASA satellites, Terra and Aqua spacecraft, which are on orbit since 2000 and 2002 respectively. So now we have 20 years of acquisition of MODIS, which build up a strong, big database of thermal emission for each volcano. The resolution of MODIS is 1 kilometer at Nadir, and it provides approximately 4 images per day. So it is not especially designed for volcanology and nor for to detect very fast events. So it's more properly designed to, in this case with MIROVA, to monitor and to follow mid to long evolution of effusive eruption. One feature that has the MODIS is the presence of a MIR channel at 4 microns, which allow to detect also very strong events without saturation problem. And this is very useful, especially for effusive basaltic eruption, which commonly saturate very easily some sensor. The raw data of MODIS ingested by MIROVA are provided by the LANS MODIS system, and these are available in 1 to 4 hours from the acquisition. This is the essentially the delay we have between the acquisition time of a satellite image and the delivery of our product, which are or the thermal anomalies or the discharge rate, because the processing here is subdivided in 4 steps. It's very quick. So once we have the image available on the LANS website, in a couple of minutes we are able to track for the presence of the hotspot, calculate the radiant power of the hotspot, and eventually, as I will show later, we can convert this thermal flux into lava discharge rate. All these steps, except the calculation of discharge rate, are automatic, and the output are sent to the MIROVA website. This is the home page where we have the map of all the observed volcanoes, and we have a list of the latest hotspots detected, subdivided with a colored power scale, which is based on the absolute thermal power in terms of megawatts detected. So the color scale here is essentially based on an absolute scale of thermal magnitude. We can call it in this way. And this scale is subdivided into 5 levels, from less than 1 megawatt up to more than 10 gigawatts. So you can see the large range which is allowed to be detected with this system. Here I give a brief overview of the product delivered on the website. We have one screenshot, is this one where we posted the latest 10 images together with the volcanic radiative power here, and the zenith angle and the azimuth of the satellites, in order to have an idea of the viewing geometry of the satellite. Clearly, we have the time of the acquisition. And this image is especially used because we don't want to have only a number associated to an acquisition, but we want to see what the satellite has detected. This is because, for example, if we only look at this number, we don't know if the activity has decreased or if it is an effect, as in this case, of a cloud. And so we want always to see the images possibly in real time as soon as they are processed. In addition to the images, we plot the volcanic radiative power time series. Here we have 1 month of time series, and in the lower panel we have 1 year. And this is clearly useful because also we don't want only to see the number, but we want to have a quick overview of the trend, if it's increasing, decreasing, or if it's stable. Since the magnitude can change over several orders of magnitude, we provide the time series typically on normal scale or in logarithmic scale. And here you can see the example of Fuego in Guatemala, when we can see some pulses of thermal activity and associated to the level detected by MODIS. Also, another important information is the distance from the hotspot, from the summit, and this is the example of Ertale. And this is useful, for example, to monitor and to track the lava flow advance. Clearly, this is possible only for large lava flow because the resolution is 1 kilometer. But as you can see here, for long-lasting effusive eruption, this can be very useful because we can see the period of lava flow advance, and after this, the lava flow front stagnated at in the distal position without advancing. And also, this is also useful because we can see some spots here, some spike of the thermal anomalies very distant from the summit, which are associated to fires or false alert. And so we can have an idea quickly of some false thermal alert, which is not related to the eruption. We also provide the data in Google Earth format, and here you can see an example at the beginning of the Holuran eruption. The acquisition of all these images allowed to track the advance of the lava flow, and so we were able to estimate the velocity of the lava flow front advance, and together with the trend of the thermal flux, clearly. And finally, this is a new, this is a new product. We add also the analysis of Sentinel-2 images, which has a 20-meter resolution in the SWIR channels. And here you can see that we combine the red dots are the number of pixels detected with the Sentinel-2, and the blue lines is the thermal flux from Mirova. And so we can correlate the low spatial resolution of Mirova, but with the good temporal resolution, with a high resolution image of the volcano. So we can say, okay, in this case, this thermal flux is due to the activity, in this case, it is Etna of the northeast and southeast crater. And if you can see how this can evolve during time, we can also appreciate much better the increasing, for example, trend of thermal flux due to increased activity at the summit vents, as well as the occurrence of lava flows and or other volcanic activities. So we have three kinds of information, basically, which we can provide automatically on the website. Clearly is the presence of or the absence of an hotspot. And this is the example of a few months ago, at the beginning of the eruption of Soufrière de Saint-Vincent. On 28 December, we detected for the first time a thermal anomaly, which was related to the emplacement of the lava dome, which sadly is now exploding. And as you can see, MODIS detected the first thermal anomalies on 28 December. If we wait for high resolution, we had to wait until 3 of January, so 5 days later. So it's quite important in terms of timing, especially for volcanoes, which clearly are not very well monitored as Etna or Piton de la Fournaise, where the satellite images are one of the unique tools to detect the presence of thermal anomalies inside a crater, for example. So the other information is clearly the intensity of the thermal anomalies in terms of radiative power and the trend. Here is an image of Fuego, and you can see, for example, at this time, there is in the days before a very initial trend of augmentation of thermal activity, which appeared in the last week of activity. Now, if we compare these on the previous year, we can see that this is the result of some cyclical behavior of the volcano, which already occurred several times during the year. So at this time, we are more confident that probably there is the beginning of a new cycle, and this moderate thermal activity clearly has to be taken into account quite importantly, because it could be the beginning of a new cycle and a new paroxysm. If we extend this on longer time series, for example, for Fuego, we can see how important it is to have a huge data set of thermal data to interpret the current activity. So the building of a large data set of thermal data is one of the main focus now of the Mirova project, in order to have some statistics for each volcano. And finally, clearly, the location also here is another example at Klucheskoy in Kamchatka. About 1 month ago, there was a reprise of the activity, which Klucheskoy was already in activity during the past year. But in this occasion, the Sentinel-2 data allowed us to detect for the first time in 20 years that the effusive activity was not on the summit, but on the northern flank. So this is clearly another very important information to be provided to the observatory about the displacement of an effusive activity. Here I summarize some best practice in using the website directly for the observatories or for the user. And the first is clearly to look at the trends instead of a single image. And this is the example of Papaya, where we have a thermal anomaly of 200 megawatt, which is quite low compared to the previous one. So it seems apparently that there is a decreasing trend. But if we look at the longer time scale, what we suggest is to wait sometimes and to confirm a thermal trend, because there are several factors which may affect one single image, such as clouds or the presence of plumes or the satellite viewing geometry. And this is the second best practice I suggest, which is always to look at the images and discard the images acquired in cloud condition or with very high zenith angle. And so to build, eventually to build up some table of the time series of volcanic radiative power, but to add a column of a quality check and exclude for the time series the bad data. This provides a more robust trend of thermal anomalies, which, as we will see later, can be used to estimate diffusion rates and lava flow volume. So this is an example, for example, at Piton de la Fournaise. This is the eruption of August 2015. We have unsupervised data. Here are all the data as are acquired by Mirova. And you can see here, there are two through, which we don't know if they are due to clouds also here or to the lowering of the thermal activity. And if we look at the image, we can draw the real trend. And clearly this was the effect of clouds. And this is the effect of a real change in the effusive activity, real drop, which underline some impulsive processes behind the eruption. Also, another suggestion is always to compare the thermal data and with other parameters. In this case, we compare the thermal flux with the tremor. And so we are much more confident that this is a real decrease of the fusion rate associated to a stop of the seismicity. And the same can be done with the deformation or with the SO2 data. And each comparison can help us to interpret the thermal data and to clearly to draw the conceptual model of the volcanic eruption, which is ongoing. Once we have the supervised time series of volcanic radiative power, we can build now the cumulative radiative energy. And often, if we plot the volcanic radiative energy, we can also appreciate some pattern which may become evident, which are not evident if we look at the time series of radiative power itself. For example, here we can see that these pools on longer time scale continue on a linear increase in the radiative energy. It's like if behind this eruption there is some time predictable behavior, especially during the last three phases. Okay, now just a last comment on this. Clearly, if we don't supervise the data, this is the cumulative energy we obtain, the blue line, which is clearly underestimated for the real one, because we take into account clouds, volcanic plumes, and attenuation due to viewing geometry. So it's very important to supervise the data. Now, the second part is about the conversion into fusion rate. I don't want to enter into the technical details, but only to stress that there are at least two methods which are complementary, two approaches. One which is mostly based on thermal infrared data, and the other which is expressly derived for the middle infrared data as provided by Mirova. And in this case, there is a clear relationship between the time average discharge rate and the volcanic radiative power. And this relationship is provided by a coefficient here called CRAD. Behind this correlation, clearly there is a correlation between the total energy released by an eruption and the total volume emplaced. This is only for effusive eruption. I'm talking only for effusive eruption. So a few years ago, we made some tests on several effusive eruptions all around the world to see if this coefficient, which relates the energy and the volume, is always the same. And this is the results where we have the energy and the volume. And you can see that there is some control, especially on the type of lava erupted. And possibly this is explained by the different rheology of the lavas erupted behind the coefficient of correlation. This is the main approach. So if we know which is the correlation and what is this value of the coefficient, we may convert the energy into the volume, and at the same time we may convert the volcanic radiative power into lava discharge rate. This is the case for Piton de la Fournaise. So we have 26 eruptions now, which has a good data set. So we calculated the energy of each eruption. We compared this with volumes published and measured on the field or with other techniques. And we obtained the best fit coefficient, which is this one, and the uncertainty of this approach. So now we can use this coefficient, and we may convert simply when we have the radiative power. We use this coefficient and we calculate the target. This is what has been done for several eruptions up to now. And here you can see the time series of two groups of eruption of Piton de la Fournaise, which are quite typical. One eruption which has high diffusion rate at the beginning and then a declining trend. And one other eruption we always start high, then it declines, but there is a waxing phase just before the end of the eruption. So we are building this database of type of eruption. Clearly, for each eruption, we can integrate the time average discharge rate to get the lava flow volume. And then also we can analyze the effusive trend, as for example, in this case, once we recognize this type of trend, as I will show later, we can also provide some forecast of the final lava flow volume. We have some limits clearly on this method. We don't have estimate if there is cloud. We have a high uncertainty for short-lived eruption, and we have some problem if there are fires or other heat sources which are not associated to the effusive eruption. Now I will move on the application part, and I will show some example. And the most recent example is the eruption of a few days ago at Piton de la Fournaise. The first thermal activity has been detected on 10 of April at 6:30 UTC time. And one automatic email was sent directly to the Aster urgent request protocol that Mike will show in the next talk. So we trigger an acquisition of Aster as soon as possible. And after this automatic email, also there is a manual email which has been sent once this data has been checked. And by checking, we noted that there was cloud around the thermal anomalies. So the estimation of effusion rate is probably an underestimate. And this is commented in the email directed to the observatory and to Oriel to run the lava flow model. Since a few years, we developed a protocol to follow the eruption. So we compile a form like this one, where we write the date and times of the acquisition and the minimum and maximum TADR, and we provide a graph with the effusion rate trend and the cumulative volume trend. This protocol is inserted into an effusive crisis response, which will be also the subject of the next talks. I don't want to say more about this, but we provide some hazard map of the lava flow based on the effusion rates provided by Mirova or other systems. This is the example we typically has at Stromboli, and this is a report during the 2019 eruption of Stromboli, and this is the information we provide to the Department of Civil Protection. We provide the current effusion rate, the volume erupted since the beginning of the eruption, a comment about the trend, which in this case was augmenting during the last days. And thanks to the Sentinel-2, in the case of Stromboli, also we are able to see the length of the lava flow and if it's arriving to the sea or if it's confined to the upper part of the Sciara del Fuoco. One more product which is very interesting is due to the fact that we have a robust database of the past eruption. And here you can see for Etna and Stromboli an histogram of the effusion rate, of discharge rate of 20 years. And we can see that for these two volcanoes, so we have a bimodal distribution of the discharge rate. And by analyzing with other data set, we know that the two distributions are related to the Strombolan activity for the lower regime and the effusive activity for the higher regime of discharge rate. So if we draw this statistical transition line, we know when the volcano is approaching an effusive phase. So there is the magma column which is rising, which is feeding the Strombolian activity, and probably if there is some long-term increase in the input rate, we can see this for several weeks or months before the onset of an effusive eruption. Clearly, this does not work every time. There are eruptions that start suddenly, And this is a matter of research because there is some eruption which is preceded by this thermal increase and some other not. So it is interesting. As I said, another application is to extrapolate the lava flow volume from the initial measurement. This is the case of Holuran eruption in Iceland in 2014. We extrapolated the lava flow volumes after 40 days of data. And this is the final volume we get, about 1.5 kilometers cube. And for example, this final volume is used by some model like Mr. Lavalova, which require the final volume to be run. And this is the result of the model by running the model for 1.5 kilometers cube. And this is the comparison with the real shape and thickness of the lava flow at the end of the eruption. And finally, another product always which can be depicted from the trend is, for example, we may have an idea of the imminent end of an eruption. Also, in this case, is the case of the Holuran eruption in Iceland. We have a slow decline for several months up to the end of January 2015. And since this date, we start to see a sharp decrease in the effusion rate, and 1 month later, the eruption was over. So this changing point is quite interesting, and now we start to observe this particular pattern in other eruptions, especially in large effusive basaltic effusive eruption, and probably this may reflect some process inside the dike, and the monitoring of this changing point can be used to make a forecast or to draw some end of eruption scenario. A last slide about the issue to be solved. The supervision of data is quite important, and it would be very useful to make it automatically. So some possibility is to develop some algorithm for estimating the effect of clouds on viewing geometry, or to use artificial intelligence to supervise the data set, or to provide the full data set on a web-based tool, and the user directly may supervise the data. So it's the user that select which data can be used to estimate diffusion rates. How to deliver the data? Also, this is an important issue. Actually, all the data are delivered manually after checking from our side, but we could evolve into an automatic email which send automatically the time average discharge rate and volumes, but this is linked to this point. So we need to be able to supervise the data automatically, or to provide some web-based tool to select the data. And finally, as I said, it's very important to build a robust database of past eruption to calibrate the coefficient to estimate the effusion rate, and also to have a database of typical effusive eruptive trend, or the threshold for the transition between strombolian to effusive activity or to paroxysmal activity. And so it's very important to continue to monitor in this way the future eruption, and the transition to VIRS is one of the best solution. And here only a last slide. This is the Ertale eruption. This is what we detect now with Mirova, and this is what we can detect in the future by using VIRS, which will be on orbit, at least I hope, for the next 10-20 years. So we could, and this is the comparison of the cumulative curve, which are quite very good. So we will able to continue to monitor in this way for the next 10-20 years, and to make the database of Mirova grow for much better estimation of effusion rate at these volcanoes, but also at other volcanoes. Thank you.
Thank you very much, Diego, and thank you for keeping to the time. That was a perfect 30 minutes. Does anybody have any questions for Diego?
I think Stefano have one.
Stefano.
Yeah, Diego, do you hear me?
Hi, ciao
Hey.
Stefano.
Hey, ciao, Diego. Yeah, I have a question just for the new implementation of Sentinel-2 in the Mirova system. So what is the role of Sentinel and the benefit that you can bring Sentinel to your system that is already very good, I mean?
Okay, yes, the main aim is to have an idea of when we detect a thermal anomalies at Etna or Piton or other volcanoes, what is the source? Because we have some volcanoes where we know what is the source. For example, at Piton is probably a lava flow, but in many other volcanoes, we don't know what is going on. And clearly to have an high resolution data set which provide us this information is very useful, and Sentinel-2 is quite good. And for example, at Etna, we may know if which of the craters is now producing the thermal power which we are detecting with Mirova. And the other is to try to merge different kind of sensor which acquire on different wavelengths, such as Sentinel-2, which works on SWIR data, but to provide the same, to check if we can provide the same trend and the same parameters. And from the first analysis, yes, because the area detected by Sentinel-2 and the radiative power detected by MODIS with two resolutions, with two different wavelengths, they provide the same results. So they are not contrasting. So if one is increasing, the other is increasing, and is increasing of the same amount. So we know that we are more robust in our numbers that we give. And also we can add, for example, for Sentinel-2, we can add an information which is the area of the lava flow, the actual, the active area, which we don't know from MODIS. We only know the thermal flux, but we don't know the area or the temperature. And with Sentinel, we know the area, so we can also have an idea of the temperature. So in reality, we can provide some second order of product by merging high resolution and moderate resolution data.
Yeah, see, thank you.
Thanks, Diego. I see Oriel's got a hand in the air.
Yeah, hi Diego. I wanted to know why on the Mirova web page, why don't you add there, or is it possible to add directly the effusion rate? Because we can see the radiance and everything, but this is not a data you are sharing like this. You have to send this manually. Why not putting it directly on the website?
Yes, okay, because there is one motivation is the supervision of the data, because we prefer to provide the effusion rate once the image has been checked for the effect of clouds or satellite viewing geometry. And also because Mirova now, the website, it works for 200 volcanoes, and the conversion between effusion rate, between heat flux and effusion rate cannot absolutely be applied to all the volcanoes. So we first need to calculate the coefficient, and then we need to be sure about the type of activity, because the thermal proxy can only be applied if the thermal anomaly is produced by some effusive activity. For example, for a volcano, if there is some new lava lake activity inside the crater, we cannot provide an effusion rate because there is no lava which is going out. So if we don't know what is going on, we cannot transform the heat flux into effusion rates. And the same for explosive eruption. We have thermal anomalies due to the destruction of a lava dome. And it's dangerous to convert that heat flux into an extrusion rate. Now we are working on this, but it cannot be done now automatically on the website. So the the only data which we want to share is the heat flux, but then to convert this into effusion rate, we need some interpretation. And this is not possible actually automatically. We can do maybe in the future for some volcanoes, for example, Piton de la Fournaise or others, but probably in some other web-based system specifically for giving effusion rates. So where we have calibrated the coefficient, and when we will have find a way to supervise the data automatically.
Thank you, Diego. Lucia here has a question for you as well.
Yeah, ciao Diego. So speaking about Piton de la Fournaise, this morning we saw Hotwalk that can record the signal every 15 minutes. And then there is your system that is slightly different. Can you explain the audience how do you do the integration when there is a crisis? Because I know that both you and Matthew concur to give data to the observatory, and I think it's great because the two systems can really add the whole picture. Unfortunately, yes. I don't think Matthew is there. I don't think so, but yeah, can you explain the audience this approach?
Yes.
I like this way of combining things.
Okay. Yes, the two system works on different raw data. So the initial data is different because Hotwalk is based on a geostationary satellite and provide the data every 15 or 30 minutes, but with a lower resolution. So it's very good to detect very fast events, which are absolutely hidden, not hidden, but not detected by MODIS, because for the temporal resolution. So very fast events are often lost by Mirova, but detected by Hotwalk. On the other side, due to the resolution of Hotwalk, which has much bigger pixel size and a viewing angle, which not always is favorable to the lava flow, the detection limit of Mirova is quite lower. And so we can detect a small thermal activity and as a consequence, small effusive activity. So there is some threshold, which I don't know exactly where is, but probably is around 1 meters cube or half a meters cube second, where it's difficult to detect an effusive activity with Hotwalk, but is possible with Mirova. So the two clearly, if they are merged, they provide a very accurate estimate for fast and strong eruptions, and the other can provide very good estimate for low intense eruption. But for example, we could last for several. Is not the case, for example, of Piton de la Fournaise. But for example, at Stromboli, we don't see thermal anomalies with a geostationary satellite, but we can monitor some change in the Strombolian activity with Mirova. On the other hand, we don't see exactly the start of a paroxysm at Etna, which is on the other side detected by Severi and by the geostationary satellite. So we see different kind of activity, and when the activity is long, sufficiently high, and temporally constant, we provide the same results.
Thanks, Diego. No, it's good to give this overview for everyone that's listening to us. Thanks a lot.
Thank you very much, Diego. We'd better move on. But what your talk did show very nicely, Diego, and I thank you for this, is also, I believe, an unrest point that today with satellite thermal remote sensing, we're at a point where for MODIS, for example, we have almost a quarter of a century of data now. If we add AVHRR, we've got 50 years of data. So we're at a point where we can make really robust baselines and also really robust event detection and definition tools in terms of shape of the eruption rate curve that Diego showed us. So thank you very much, Diego, for showing that, and for also setting up Mike Ramsey for our next talk, who will be presenting ASTER and the Urgent Response Protocol. Oh. Over to you, Mike.
Thanks, Andy. Share this. Okay, hopefully everyone can see the presentation. Andy got the name slightly wrong, so I won't give him too much grief for that. It's Urgent Request Protocol, but that's fine. I want to thank the conveners and those of you listening in for this talk. I actually had prepared this slide last year. You notice the date on the bottom, but unfortunately we are a year later and we are virtual. I'd much rather be giving this talk at Reunion, but I sit here in my office at home. Okay, I want to give some discussions and some background on this program using this ASTER sensor. And we'll go through exactly what ASTER is and how this program evolved and where it may go in the future. Again, thank you to Diego for giving some hints to this program. So as you heard, ASTER, or MODIS, which is also on the same platform as Terra, has been on orbit now for over 21 years. And it's often given the nickname as the zoom lens for MODIS. So we are not a sensor that is able to do rapid response. But the idea of this URP program was to improve the resolution to a degree where it might be useful to new eruptions. So what I'd like to do is go through a little bit of the history of ASTER specifically for volcanology. The wonderful thing about this sensor is the science team, original members back 20 years ago, all the way through to current science team members, have had a strong linkage to volcano science. There's always been a priority for this sensor. So I will talk about some of that and some of the current statistics. I'll then kind of dive in a bit to this URP program and show how we link with MODIS more rapid response systems like ModVolc and Mirova. And then I'll talk a little bit about some conclusions and future possibilities. So ASTER itself, again, was launched in December of '99 on the Terra satellite. The image here is Ale with the visible near-infrared bands at 15 meters per pixel. And this was actually the first image acquired in the test phase of ASTER on orbit. So that leads us into a sort of a long history of targeting volcanoes, which has been quite nice. So originally ASTER had 3 different systems. As you can see, and probably most of you who ever used the data know, the SWIR channels, unfortunately, that system failed back in 2009. Again, this was supposed to be a 6-year mission, and we are now on year 21. So we're quite impressed at the system itself. In red, I show the TIR, the thermal infrared, and I show that in red because that's going to be the focus of what I want to talk about today for the most part, and especially for the science I've done. This is the first time we've really had multispectral to this level on orbit and at that spatial resolution. So normally, this is a 16-day repeat time. We've had 3.5 million or so scenes acquired in 21 years. And actually about 11% of that archive is focused on volcanoes. So there's quite a few scenes in the archive, most of which has not been actually examined for science. That repeat time improves toward the equator. So we high latitudes, we'll get that to about 5 days. And again, there were many original science goals. This is not a volcano-specific instrument, even though we try to make it that. But specifically for volcano science, it was noted early on that again, this multispectral thermal infrared, routine acquisition at night of thermal infrared, which had not been done before, the ability to generate along track real-time DEMs with the visible near infrared data. There was also multiple temperature gain settings to try to avoid saturation, and obviously the higher spatial resolution. When we put the thermal infrared image over that, this is why I get back to the 5 channels. This is a decorrelation stretch of that same scene, but the thermal infrared data, and we start to get at compositional information. So the thermal infrared is quite good at picking out silicates, carbonates, sulfates, and obviously elevated thermal detection. So we can really start to wrap in geologic mapping in with the hotspot detections. Publications have increased obviously over time. This is a paper that I did with a student of mine last year. Not as many clearly as a larger system like MODIS, but still an interest in using Aster for volcanic applications. So as I mentioned early on, even before launch, there was this system in place of recognizing some of these benefits that I list again in this first bullet. And that led the original science team to create a very specific observation strategy for volcanoes. Now, recall, or I'll note here that Aster is not on all the time. This is what I say here with this 8% duty cycle. It's not a system like MODIS that is on just continuously acquiring data. So the images themselves, the targets on the ground have to be scheduled. And that really does cut back on the repeat time, how fast we can get observations. And this is going to bring me to the point of the URP here in a minute. So this idea of these science team acquisition requests, there's one for volcanoes, there's one for glaciers, there's quite a few of these that are recognized high priority targets. So in this original program, about 964 volcanoes were subdivided into 3 classes, and this is the observation strategy that in the higher priority targets, every 48 days, they would get an observation, every 32 days at night. So daytime, nighttime. That's still not a lot of observations. If you kind of do the math and average this out, that's really about 18 observations per year maximum for the higher priority volcanoes. So we're not going to be able to do nearly as much with tracking trends with that level of observations. However, that observation strategy has persisted for 21 years, and it produces about 16,000 volcano-specific observations per year, which is still quite a large volume of data. And we have approaching 325,000 now individual scenes over the mission lifetime. And again, it's these 3 classes of volcanoes, but as Diego noted, and even more problematic for these higher resolution data sets is, well, if you're acquiring 16 observations per year of your volcano of interest, some percentage of those is going to have clouds, changing in eruption status. What if a volcano that's in class C suddenly erupts and becomes a high priority? How does that change? There's some questions about this, how this volcano star operates. Horizon in 2011 did a study after sort of 11 years on orbit. This is his database webpage image here on the right. About 77% of the volcanoes in the Aster database had at least one daytime image with less than 10% cloud cover. So that's a relatively high number, but this is a relatively low number, just at least one in 11 years. So that's not terrific. There were many that had dozens. And the paper, the reanalysis we did some 8 years later, the average number of scenes per volcano were about 146 in the day, about 185 at night, still 7 to 9 observations per year. So this is the issue we're facing. So that brings us to the description of this urgent request protocol. This began way back in 2005 as a connection with the Alaska Volcano Observatory using AVHRR. So we were only focused on the Aleutians and Kamchatka, and I'll show you some examples throughout this talk of volcanoes in this region. And the simple point of this was rapid detection with something like AVHR and eventually MODIS. Can that trigger the system that would schedule the next available observation of Aster? So the graphic here is detection of a hotspot in the Aleutian Islands by, at the time, AVHRR. The system is enacted, uploaded to the Terra satellite, and the next time Aster was coming over that target, it would observe. So this takes away the uncertainty of trying to schedule this or trying to pay attention to volcanoes that change status. Our goal was to just sort of operationalize this system of scheduling Aster data. It's a large integrated system of several universities, volcano observatories, NASA, USGS, Japan Space Systems, and then others. And it relies on, again, the detection by these high temporal, low spatial resolution sensors. They trigger the response and improves our observational frequency, sometimes to as low as 1 to 3 days. So we end up with quicker response time to data, and importantly, when there are ongoing eruptions, this system is just continually re-triggered. So we get observations every single Aster overpass, and we can use that to look at kind of large effusive eruptions like the Kobachek eruption in 2012 or the 2018 eruption of Kilauea. Again, I'm going to highlight the multispectral capabilities where we can then start to track sulfur dioxide plumes, compositional variations, et cetera. And then, although somewhat effusive, but explosive eruption of the Shirashima volcano in Japan back last summer, we had an excellent series of observations, particularly clear. And this is work by Daniel Williams, paper about to come out, using the multispectral thermal to track ash particle size in these plumes. So back to the same slide, and this is an image that I borrowed from one of Diego's papers, I believe, showing just kind of the difference between how Mirova sees its detection versus the system used by Modvolk. So in and around 2011, we transitioned to the Modvolk system for global volcanoes, and then we added Mirova a few years later for a set of targeted volcanoes that we're using. So what this does is produce somewhere between 30, our maximum so far has been 61 additional images per month. So at least 1 to 2 new scenes per day of volcanoes around the world. And what we've done most recently is now started to add ground-based triggering systems. We are in a test phase. Actually, it's pretty operational now with INGV for Mount Etna using seismic triggers. So again, the goal here is to acquire images at a higher spatial resolution for doing some of the things that Diego talked about with, say, Sentinel data. This is one of the pages for this system. The URP system doesn't have a large front page like Mirova does. Most of this operates kind of behind the scenes. This is a system page at the Land Processes DAC in Sioux Falls, South Dakota. And mainly this is used for my tracking and those who use the system. So we see the operational systems listed up here, the most recent trigger. This is displayed graphically in this, with each one of these tick marks being a trigger that's sent in. We also have the capability to do this manually if something happens that we haven't seen automatically, so we can put that in as well. It displays the Aster schedule page of observations that come in, sometimes up to about 6 per day. And then there's also a map system that we use that will show the current position of the Terra satellite, and then all of the volcanoes that are currently being observed through the URP system and their various states. So these are not states of activity, but these are states of scheduling for the system. And this helps me keep track of what targets are about to be acquired, which ones have been completed. So just, I want to show just a couple most recent examples. The Iceland eruption is one of those. Right? And so if we have a daytime scene, Aster is showing us the 15-meter data of the eruption, and then on the right-hand side are the 90-meter pixels in the thermal infrared. So these kind of data sets, when they're acquired, are sent immediately to any ground-based personnel using the data or systems that are looking at these kind of data sets. Another example from Sheveluch back in 2019. So as I mentioned, at higher latitudes, we get nominally better observations anyway. At these latitudes, we can often get observations in 3 days. We call them triplets. We can get a day-night scene in the same day. So this is a daytime image of Sheveluch volcano with the VNIR data draped over Google Earth. And then I can this is the thermal infrared from that same scene. And we go from April 20th, 1 day later, and then about a week later. So we can use these data sets to look at various dome collapse events, thermal anomalies running down the different washes and how the dome itself is changing over time. One of the things that we've done is going back and look at some of these retrospective analyses. And this is an example from the Reith et al. Paper, modified graphically a bit by myself, just to show astrothermal infrared of Kluchevskoye 2007 eruption, how it changed over the course of several months. These data sets in orange are Aster kind of in its normal background state. It then becomes triggered and we start to get more observations. It's not until much later that the hotspot becomes great enough that ABHR data is usable. But the point here is that with the data sets in a more rapid acquisition, even once a week, we start to see these kind of thermal fluctual variations leading up to an event. This is especially important for small craters, dome-forming eruptions, things where, again, there's may not be a lot of other detections or activity changes. 2 years later, Kluchevskoye eruption, again, typically in Kamchatka, multiple thermal anomalies are detected at every overpass. I just showed the Aster VNIR eruption image, and then here the shortwave infrared data, which unfortunately we don't have anymore, but the ability to acquire data every 12 to 13 hours, we start to see changes in lava flow and lava flow propagation and being able to use that to calculate velocities. In the most recent image from just last month, Diego showed this image for Modus, the flank eruption detected as well from the URP. So I want to end or kind of just finalize with going back to Piton de la Fournaise and the image that I showed at the start of the talk. It's a focus of Andy's paper in 2019. And then I'm just showing another image here from a paper by Daniel Williams and myself for mapping this volcanic ash, but importantly also using the Aster DEM to get the plume heights as well as the ash particle distributions. So what I'm going to show for these next couple slides are just quick screen grabs, because this is what we were doing during this eruption. Every Aster image that came in, I generally just did a quick processing like this and sent this image to Diego, Andy, Oriel, and the folks at the Volcano Observatory. And this is just a grayscale image of the Aster VNIR, zoomed in here just to get vent locations. Not so much for the temperature, although we did do that. This is the thermal infrared for that same scene. We start to see the lava flow propagation. And then we can go a little bit ahead in time. This is 5 days later, the propagation of that lava flow. And then this is a highly stretched, saturated image from several days later. And mainly we were just using this to the slight color change in the newer lava flows seen in kind of silver versus the older lava flows down here. So we were looking at kind of where the flow front was and its propagation over time. And this was a image that appeared in Andy's paper showing kind of our time series of just some of the images we acquired. So again, Piton de la Fournaise is not a high latitude volcano. So we were pretty happy with some of these observations, especially considering the cloud cover that we often see in this region. So even at these lower latitudes, we're still able to get images every 1 to 2 days with then some gaps after that, but we can get a few good images that way. So I'll finish here with just some information from this paper in 2020. And what we did was go and this is ended May of 2019, so about 2 years ago now. We did a deep analysis dive into the archive, looking at just 10 volcanoes for 1 year, 4 volcanoes for 5 years, and 1 volcano for all 20 years. Total of about 2,100 scenes. All of these were inspected manually. And we wanted to go through different compositional types, eruptive activity, climate, et cetera, latitudinal distribution. And all of that, about 53% success rate in detecting volcanic activity. What does that mean? That means the rest of that was likely cloudy, or potentially some issue with the sensor not acquiring, but most of this is clouds. And we saw plumes, flows, hotspots. This 87% potential miss rate sounds worse than it is. This is essentially saying if we had a sensor like Aster that acquired at the same rate as a sensor like MODIS, we would get 87% more observations with a sensor like that. The URP implementation drove down the days per scene from about 20, just using the volcano star, to about 6.5 using URP, so an improvement of 215%. But we have this fundamental limitation of a single scheduled higher resolution instrument. Again, this is not an image sensor that is on all the time. I won't go through this in great detail. This will be available if people want to look at this. It's also in the paper, just to show you the volcano names, the number of triggers that we got from Morova and MODIS and MODVOLC, the number of scenes, the number of events, our detection percentage, and our cloud percentage. Some of these are quite small, like our Daale, and some of these are obviously much higher in targets where there's a lot of clouds. This will switch here again to this miss rate, which is, again, if we had an observation, a sensor like Aster observing at the same frequency as MODIS, we would get a lot more data. So in conclusion, we would argue that there's been sort of this paradigm shift with Aster, now 20 years old, but back then, it was quite a novel new instrument. Well over 3 million scenes acquired, 10% of which are focused on volcanoes. Greatly improved spatial and spectral resolutions, particularly in the thermal infrared. And again, these ongoing programs to improve the temporal resolution of Aster. But ultimately, we are limited by the instrument itself, how it schedules and how it observes. We have great success in some higher latitude volcanoes where we've done observational triplets every 5 days for eruptions that have gone on for 6 to 8 months. But again, we have this large 20+ year archive, most of which has not been analyzed at the level of detail that it should be. We are using it to look at sort of precursory studies, what's happening with volcanoes prior to a known eruption. Also for future mission planning, what kind of instruments, thermal infrared instruments, should be considered after looking at this 20-year archive. So 2018, NASA Earth Science had this decadal survey, comes out every 10 years, and there was a very specific focus on thermal infrared, on hazards, and on volcanoes themselves. And in red, it said there should be new TIR data that's multi to even hyperspectral with revisit times of hours to days at sub 60 meter spatial resolution. That's a hard thing to do. It's going to be challenging for NASA to try to, or a combination of NASA and other space systems, countries to do that. Could be achievable, however, with several lower cost small satellites, and particularly using the same technology we would use with ground-based thermal cameras. That would improve and be a cost-effective way of doing this. And some of us on this meeting have proposed such a mission that's currently under review by NASA. So I will end there, I believe, and happy to answer any questions.
Thank you very much, Mike. Does anyone out there have any questions? Following up from the last presentation by Diego, where we finished by mentioning what powerful baselines for unrest we can now create from the orbital perspective. Do you want to make a quick comment, Mike, on our ability for baseline creation using archives of high spatial resolution data today?
Yeah, that's one of the, I think, the most interesting things now that we have such an archive. Now, obviously, we haven't, but scientists could integrate this with the sparser but longer temporal resolution baseline with something like Landsat. But even with 21 years, and even with a system prior to the URP, if we were just looking at the volcano star, a lot of these volcanoes have been persistently active and hotspots that are detected throughout the entire 21 years, even to the point of very small, subtle thermal anomalies. So I think that's one of the greatest benefits of something like ASTER is we can see a 1 to 2 degree change pixel integrated over a 90-meter pixel. So we can really start to tease out the very small scale thermal variations and where that may change. And I think we showed that with that Kluchevskoy example where it was hovering and just a slight change of about 1.5 degrees Celsius started this several month pattern of fluctuating thermal variations. So I think we have this for hundreds of volcanoes that we have not really examined yet.
Great, thank you again, Mike, and thank you for getting up maybe a bit earlier than normal to join us this morning for you, this afternoon for us, this evening for a few others. So with that, I'll pass on now to Auriel and Pierre to move on to lava flow modeling. So will it be Pierre starting?
Yeah, Pierre will start actually, and then I will do the presentation in the second part.
Great, I'll leave you two to tag team it from here on. Thank you.
Pierre, you can put your mic on, maybe. Pierre, ton micro. Okay, I think now we hear you.
Do you hear me?
Yes, perfect.
Okay. So I present lava flows on response to during volcanic crisis at Piton de la Fournaise. It's a two-part talk. I will start with a SHALAVA, a shallow water mathematical model. And then in the second part, Auriel will present you a downflow for a simulation of channelized flows. It's a joint work with Noé Bernabeu and Andrew Harris. So SHALAVA is based on the mathematical formulation of a 3D Bingham rheology. Bingham rheology, it's a non-Newtonian flow. It involves yield stress value, sigma 0 here. So in terms of mechanics, the Cauchy stress tensor sigma is related to d of u here, the rate of deformation tensor with the viscosity parameter here, eta. And there is an additional yield stress term, which is specific to the Bingham rheology. And when the stress is less than the yield value, there is no flow, the fluid is at the rest. It's a so-called arrested state. For instance, the lava flow stops down in a slope. And we consider here a special case when the flow rate is much smaller than the length of the flow. It's a so-called shallow water approximation for viscous flows. And we obtain, instead of a 3D model, a 2D surfacic evolution equation for the flow height H with respect to the two horizontal variable X and Y here. And so I will turn to a practical application. It's more concrete. And here is an example for the Piton de la Fournaise. It's a 2010 lava flow. It's a complex lava flow with several events and branching of flows because of topography peaks like here. There is several different branch of flows. And here it's topography, numerical topography. And we consider only part of the volcano. Here we can observe a specific complex topography with small peaks. And this peaks is responsible for a two branch of the main flow. And there is also several secondary branch here. It's a arrested state as observed by the observatory of the volcano here. And here it's the Chalava solution computed. So we can observe with a thin white line the observation from the observatory. And the color maps indicate the Chalava prediction by numerical computing based on the Bingham rheology. Here in colors, it's a flow height. And it's a time-dependent simulation. We can observe at each time step the flow. And here it's after 5 hours. On the next steps here, we can observe both the flow height on the left and the temperature field here in Celsius degree. It's this color map on the right. And then at the end of the flow finished to stop. In the stop due to Bingham rheology, it's a full stop. And we can observe in gray, it's observation of the observatory, it's a data observation. On the color map is the simulation. We can observe the not so bad agreement between both. There is branch flows, but here there is perhaps more extension, there is small discrepancies. Perhaps due to uncertainties on the topography. And I now turn to an extension, the effect of forest on the lava flows. Here you can observe lava trees. It's during the lava flow, trees are burning, but it remains an array of cylinders like that. It's so-called lava trees. And this changes the flow rate because there is an array of obstacles. And from a mathematical aspect, this 3D array of obstacles is replaced by a continuous equivalent medium, a kind of a porous medium, by a mathematical analysis, it's homogenization. And we obtain now, instead of a 3D array of obstacles, we obtain a 2D evolution equation for the flow height with the two horizontal variable X and Y here. So it's a reduction of the complexity of the model. And we start by a validation, by a comparison with experiments in lab. Here it's a carbopole flow with an array of obstacles here at the center. And carbopole is a gel, so it's fully stops here. There is no more flow, but there is a difference of height between the left and the right. It's a final position. And we perform several simulations. There is first in a red line is experimental observation. And there is two 3D simulation. One with a full array of obstacles, the second one with a Darcy porous media equivalent 3D model. And here it's a Chalava simulation with a reduction of from 3D to 2D. And here it's a dark black line. and we can observe the good agreement between both their simulation. But the difference here, Shalava took only 3 minutes of simulation on a laptop, while the full 3D simulation with obstacle took several days on a supercomputer. So it's a very huge reduction of computing time. And now we apply it to the forest effects for the Kilauea in Hawaii. So here is on the left the simulation without any forest. It's a false simulation because in reality it was a forest. So we can observe there is a very thin line, thin white line. I don't know if you observe it. It's a very thin line here of the real observation. And without forest, we go, there is too much extension. And when we take forest into account in the model, there is a reduction of the extent of the flow. But the flow is very small discrepancies, and perhaps there is due to also uncertainties with the topography. There is a problem with forest and evaluation of a right topography before the lava flow. And in conclusion, I present Shalava. It's a free software. You could download the source code on the user's manual. And here is a link to do that. It's a general mathematical model. You can enter any complexity of topographies, and we are able to predict complex branching flows on a very complex situation. It's also efficient in terms of computing time. The more complex topographies took only a few hours of computing time. It's less than the real-time lava flows. Most of the time, the lava flow takes several days. So we are able to predict the final deposit before the event is finished. In perspective, the main step is now a transmission from the mathematical community to volcanologists in order to integrate it in the standard tools, and also to consider more applications on practical validations. And if you are interested, there is more reading, several papers in journals and book chapters. And also, Shalava is built on the top of the Reolef FreeFem C++ library. It's also C++ free software. And here are some preliminary computation on Python de la Fournaise in 2018 with a flow in the enclos along the wall. Here you can observe this extent. And also another preliminary computation with the Etna lava flow. Here is the observation, and with the secondary branch of flow. On the simulation, here it's a straight flow. There is no branch. Also, perhaps it's a discrepancy is due to uncertainties with topography. It's a main challenge to have very accurate topographies. And so if you have one or two questions, we can talk it, or or Yael will continue this talk. Thank you for your attention.
Are you good to take over, Auria?
Yeah, should I go on? Okay.
Yeah.
Thank you, Pierre. Maybe I'm now realizing that maybe I should have present first to put a bit more context into that. How I will show now the modeling with Downflogo that we do at Python de la Fournaise that you heard since this morning. And actually a step forward would be to use more mathematical or physical model as the one Pierre just showed. So the Shalava model, which is working quite well, as you can see, has not yet been calibrated or done in real time for operational response. And this is a kind of a future perspective for the work we are doing. So I'm kind of going back to Python and to what we do when there is an eruption. Okay, so I think you see the big screen. I hope it's fine. So I will just go on a bit faster at the beginning, or just here because you already know all about why we do this modeling at Piton-La Fournaise and why it is useful. So numerical models for lava flow, there are actually a lot. I think we will see some over the next days from our colleagues from around the world. Some people applied in different observatory, different models. So it exists really a large range of models, of numerical models from 1D to 3D with various applications. Some are called deterministics. That means it's one solution for a given set of inputs, like the one Pierre actually showed, but also here an example that it's often used at Etna. I think we will have a talk about that by Sonia in the next days. Or here, a probabilistic model is actually downflow used here to respond to the effusive crisis at kilo last year. And also, I think the colleagues from HVO will talk about it. So if we concentrate here on downflow, so downflow is just the construction of downflow, a well-known model that was started to be done by Massimiliano in 2005 and was used over a lot of volcanoes. And Flogo, which is a deterministic model done by Harris and Roland in 2001. So we are just here doing a contraction of the two. So downflow is a stochastic model that is able to calculate the steepest descent path. And downflow depends on two main parameters: a number of runs, so how many times the model will make a run of finding the steepest descent, and delta H, which is a vertical perturbation that will be randomly applied at each pixel. So like this, we can calibrate downflow, like we have done here on Piton-La Fournaise. So we vary those two parameters in order to find the best delta H and the best N value for our lava flows. So here's an example at Piton-La Fournaise for the recent flows. And we also have done that over other flows in the past. And we'll try here to find the best fitting parameter. Once we have those, we can then use it to simulate what will be the most probable area to be impacted by the lava flow. So quick example, you already saw those maps from here, the triangle is the main vent. And then in yellow to red is actually the probability of that the lava flow can pass by this pixel, but it also shows the area that can be inundated. And if we compare after our calibration, we can see here that we reproduce quite well the top of the proximal part of the flow, a bit less the final part. But here we can also see that with downflow is just a stochastic or probabilistic approach that will calculate from the vent up to the ocean, or up to the end of the DEM that we have. It doesn't calculate the run-out distances. It doesn't calculate until where the flow will go. That is why now, to calculate that, we will use Flogo. Flogo modeling is actually based on the fact that lava flows, or at basaltic lava flows at least, are cooling limited. That means they will increase cool down and increase viscosity until the viscosity is too high to stop flowing. So to do this, we need to know what's the viscosity, or what's the change, the evolution of viscosity during cooling. And Flogo is a model that is able to incorporate many different models. So we can use here complex rheology. So basically, as most of you know, the lava viscosity depends on the liquid phase, the crystal phase, and the bubble phase. So if we take into account all this model, we can model, as we can see here on the two graphs. When we know the decrease of temperature in black, the increase of crystallinity, we can infer what will be the increase in viscosity here in green. And also, if we measure, we can also model the decrease in velocity until we arrive to this geological cutoff. That is the point where the lava velocity reach 0. So this is what we call the rheological cutoff. So FLOGO, it's a 1D deterministic model. That means we are just looking along one slope, so along the main steepest path, and we are considering here that the flow is channelized. This is important because FLOGO cannot be used on any flows or on lobe flows. It's really made or designed for channelized flow. So we assume the lava is contained in between levees, and it will follow actually a Bingham rheology. So it will stop flowing when either the viscosity is too high to let flow or the yield strength is reached. FLOGO is able to compute the heat budget, so the cooling of the flow using different models. And this is something we can completely play with. We can change if we want to just account for the conductive heat loss or radiative heat loss or convective and so on. And is also able to compute different viscosity model, as I said, either simple with 1 phase, 2 phase, or 3 phase. So FLOGO exists since a long time and has been used many times. Actually, it's the 20 years anniversary, Andy, of FLOGO. And 2 years ago, I have, with colleagues, recoded FLOGO on the Python program. So it is much more easier and practical to change everything. So that means we can really play with it and change it or tune it to fit to our lava flow or to our volcano setting. And basically what we can compute is for a given effusion rate. So here we can see different curve of different colors. Each color is for an effusion rate. Along one slope, we can compute what's happening. The heat loss, here we can see the core temperature going down, cooling, the increase of crystallization, the effect on viscosity, and therefore the effect on velocity. So we can, for different effusion rates, for a given lava setting, for a given slope profile, we can estimate when or where from the vent the velocity will arrive to 0. And this is the run-out distances when the flow will stop. So for a given effusion rate, we have the relation between the effusion rate and the distance, So in a very practical way, now you see where I want to go. We have downflow, we have the main trajectory, and along this main trajectory, we will estimate where the flow will stop for a given effusion rate. So here 5, 10, 15, and so on. And then we can compare with what we have. So in order to do this, we had to calibrate the model. As I say, we calibrated downflow, but we also needed to calibrate it FLOGO, which means which are the main input parameters that we need. To do this, we collaborated with many of the people connected today and that already talked. So here you will see the link with what was presented before, which was the validation of this integrated cellular data-driven response to effusive crisis at Piton-La Fournaise. To do this, we choose the April 2018 eruption. And why? Because we had a very good tracking of this eruption, also because it lasted for over a month or so. And we can see here some images we already saw. So we see the coherence data from INSAR. So the evolution of the lava field, also the observation with Aster that Mike just showed before, and then the evolution of the effusion rate or the time average discharge rate obtained by Mirova. So when we had this incredible data set, we used this eruption to calibrate our model. And here, just quickly example, you have an image of the modeling. So here the different paths are in blue. Before they were in yellow to red. I will explain why this changed. And the comparison with the observation, either with the outline obtained by INSAR or with the outline obtained from the field observation or aircraft, and from also the Aster infrared, spectral infrared data. So from the point of eruption, the triangle here, we knew we had Mirova data saying that the effusion rate was between 10 and 22. And by tuning our model using the lava sampling characteristic, the viscosity model, and so on, we managed to model, as you can see here, that the flow should stop in between where the two stars are, 10 or 22. And we see that this is actually the case. So like this, we could validate our model. Also, during this eruption, at one point, the lava kind of stopped at the front, and then there were a breakout, and then the flow could break from the front. And at that point, this is the graph to the right. The effusion rate was much lower, between 0.8 and 1.6 cubic meters per second. And we can see here as well that by starting now a downflow go from this new breakout, we could model again where the flow should stop. As you can see in this, is not exactly where we say will stop. There are actually uncertainties quite large. These uncertainties are due to many things. And when we try to do a uncertainty analysis and find out that given all the input parameters and uncertainty in all those parameters, the final length position, it's about 28% correct, or let's say it can vary, it's between those percentage. So it's not an exact point, and this is important when we communicate to civil protection. So quickly here, this Andy showed it. So in an operational chain of action, the start of the eruption, communication, as we saw this morning, from the observatory to us, we know where, we know the point of effusion, then we can set downflow and run the model to obtain the map. So here I give another practical example. This is the December eruption, which was the last until a few days ago. I didn't update it with the one from yesterday, but it worked basically the same thing. It was the same. Eruption start at 4:40 in the morning. Then by 7, there were a flight over the eruption site. And then Aline came back from the flight with the GPS position, and about 4 minutes later, we had this map. So here is a very important point, because those maps are very, very easy and very fast to do. It's a very simple modeling, but it allows to have quickly an estimation. And as Stefan Ren say, for the civil protection, this is very useful because they can see really in few minutes after we are back from the field, where is the flow and until where he should go. So here we could see from this map that if the effusion rate would be above 30 cubic meters per second, there will be good chance that the flow reach the walls of the caldera here to the south. And this is important because this could trigger fire. And the civil protection need to know that. The same day, a bit later during the day, we had the first Mirova data validated by Diego, which say that the effusion rate was about 18 plus or minus 6 cubic meters per second. We also had this time, and I think it was for the first in real or almost near real time, that we had the Sentinel. So I could update the map with the outlayer from the contour, the Sentinel contour. And also we could see that the effusion rate, as it was not so high, there will be little chance that the flow reached the wall of the caldera. So I could update the map and then send it as well to the observatory, head of the observatory and civil protection. And then the eruption stopped. So this was fast, it was just a 2-day eruption, but this is a very easy way and fast to respond to effusive crises and communicate. I want to stress here that there are a lot of uncertainties and limitations, and there are mistakes in my title. For example, the eruption from yesterday, here there are 3 maps, because in 2 days I already did 3 maps. The first maps was with the approximate vent location, then it was updated, and you can see from the 2 left small one that the results are quite different depending on the slope, and sometimes this can be very sensitive, as we can see here. And then there is an update this morning when we received the first INSA outline of the lava flow. So this is where the flow is right now, or almost, or this morning. And we can see that our estimation is good, but it's not quite exactly on the path that is actually made by the lava. This can be due to several things. One of the things can be the topography. I didn't check this morning if the topography I'm using is actually the 2010 topography that was updated with recent lava flows, but not with all the lava flows since the 3 last years. So this is affecting as well. And then there are also limitations that can be the lava flow behavior can change during an eruption. Eruption dynamics can change. So if right now, for example, there is a regain of activity and the effusion rate go much higher, the setting will be different, the morphology will be different, the topography and so on. So this is hard to update for now with the model we have. Also, here is an example of the October 2019. It's interesting because at this time, the flow was really threatening the road, as we can see on this journal newspaper front page. And the modeling was saying that the flow will stop 200 meters from the road if the effusion rate was 20 cubic meters per second. But as I say, there are error bars. And here I will have never say, yes, I'm sure the lava flow will not cross the road because there are error bars. So it could have done. It stopped 200 meters before. And the effusion rate was a bit less than 20 cubic meters per second. So it worked well. But once again, this answer to one of the questions we had this morning, that no, these maps are not communicated to the public because there are errors, and it's something important to be able to interpret. And this is okay to communicate with civil protection because we had many interactions with them. We had many meetings to be sure they understand the meaning and they know what are the uncertainties. And also it was all this communication with civil protection allow us to update our maps. Here I'm showing 2 maps. The first one I ever done for the response to effusive crisis at Piton-la-Fournaise in April 2018, and one of the last one. And we can see how the colors has changed, the background has changed, and this was a need from civil protection. So they formulated this need to us and we updated it. And this last one is actually the one I think we will keep now, where the color of the lava flow is clear, it's not blue like water, it's red like lava. And the background is actually the national topographic map of France. That is something easy for civil protection to read, and they used to. To conclude, we responded, we created those maps for every eruption since 2 years. We validated this protocol. We are able to produce those maps quite fast and to provide a map that show what is the area that can be impacted and until where. And this is working well thanks to communication with civil protection. And it was also operational during the COVID lockdown last year, as Aline showed this morning. But there are many things we can improve, the error bars. We need to also constrain time and advance rate, because this is something the civil protection is always asking us, until where or when the lava will cross the road or not. And then, as I said, to link with what Pierre showed before, we need to improve our modeling, or do we? This is also a question we can ask to all our experts here. Do we need to improve our modeling toward 3D, more mathematical or physical models? Or here, like here, I'm showing those 2 models, Shalava to the top or Volflow to the bottom, where we can see this nice 3D, I put it again, this nice 3D lava flow advancing. Do we need to go toward those kind of model to better respond to effusive crisis, or can we keep simple 1D modeling? Well, then there are, of course, much more perspective to improve those models and also extend to other volcanoes or compare with our colleagues from other places like on Etna or Iceland. And that's it. I will stop here.
Thank you very much indeed, Auriel and Pierre. Auriel, if you don't mind, can I have you take your questions, and I'll shut my microphone down and give Caroline a call to tell her we're ready for her to log on.
Yeah, okay. I told her she will be here at 4:30. So we still have... do we want a break or do we want questions now, as you...
Why don't you take the questions and I'll check in with Carolina and make sure she's on her way.
Okay. So is there any question for Pierre or myself about those models? Yeah, Ben, just go ahead.
Hi, again, thanks a lot for both talks. It was very interesting. I have a question for Auriel. You said that the Flogo model is for channelized flows. Are Piton de la Fournaise all channelized?
Most of the time they are, indeed, yes. Yes.
And do you have examples of lava flow where it didn't work as well because they are more lobate or?
Well, actually, this is, I don't know if I have example now in mind, but sometimes at Piton de la Fournaise is not, the model is not working so well, and this might be due to the dynamics or the morphology of the active lava flow. And this would be something to test. Then we usually, I'm not trying to use it on Paiho flow field because it's lobby and it won't work. Also, something I didn't mention here, but when we calibrate Flogo, and Andy could maybe answer to this question as well, we will use the width of the lava channel to calibrate. So we will measure the width of the lava channel on the field and try to reproduce it with Flogo. And this is how we actually validate or not Flogo. That's why I insisted with this. And also to say that it cannot be used on any flow field. It really made the heat model and the physical model behind is for channelized flow.
And does it work also for channelized like andesitic flows?
Sylvia tried, you know. I think it needs further constraint because andesite, why an andesite flow stopped? Does it stop because it crystallized, because it was too cold, or because it was volume limited? As I say here, Flogo is a cooling limited, so it works. It should work only for the flows that have a viscosity increasing and stop because the viscosity is increased, not because the volume or not because the eruption ceased. So this is something we have to refine and test. Andy, maybe you want to add something on andesite flows?
I think the current version of Flogo safety says keep it basaltic because some of the dynamic and rheological laws begin to not apply once you move it to higher viscosity systems. I did try it once on Santiaguito, and to my immense non-surprise, it didn't work. So yeah, it's very much for a basaltic channelized case where Auriel's right. The best control parameter that we can fit it to is channel width because it's the easiest thing to measure quickly and easily. And typically, once we've got that to fit, the runouts are generally surprisingly good.
Surprisingly. Is there another question? Julie, Stefano? Stefano, go ahead.
Well, I have a question that is not strictly related to this presentation, but I would like to know something more about the risk connected with gas emission from the lava.
The risk on gas emission?
Any problem with gas emission? Yes.
Well, here we are not...
not significant.
considering that for the lava flow modeling.
Julie, did you have a question?
Yes. So Ariel did show that the modeling might evolve to a 3D representation. And I wanted to know, there is some people from the civil protection on board, and all of you who are modeling already had discussions with civil protection officers. So I'm wondering if that's a requirement from the civil protection, if they're asking for this kind of 3D models, and how it's difficult for you as modelers to provide it in real time during a crisis compared to the 1D models.
So I can answer that the first part. When we are working with civil protection in La Réunion, they never ask for 3D. They ask for when the lava will get where. And this question of time cannot be answered with the model we are using now, but could be answered with some models as the one Pierre showed before.
I can answer on the computing time on a real-time aspect.
Yes.
With computing time, with a high definition of the topography, it took about 3 or 4 hours of computing time to predict the whole lava flow. On the real time is most of the time several days or 1 week for the lava flow to fully stop. So we are able at the beginning of an event to predict where it will go on complex topographies with several branch so it's a kind of 3D. In reality, it's a 2D surfacic instead, because it's a very thin layer of lava. So models are not really 3D, they are 2D on topography. We compute the flow rate on the 2D topography. In a top view, it's a 2D.
Yes.
I don't know if it's clear. Is it okay for the response?
Yes, Pierre. Thanks. Thanks. And also, what I wanted to say, yeah. So the computing times, as I say, these very simple maps is a minute or maybe 5 minutes to make happen. That's why we privilege this. There are maybe other questions from Adalbert. You want to ask something? Go ahead.
I have a follow-up question for Pierre on his answer. What are the eruption source parameters you need for your 3D for your simulation? Because maybe they are not the same as the eruption source parameter you Oriel need, and maybe some are difficult to obtain on real time. For example, volume.
So there is 2 kinds of data we need. The first kind of data is, I call it material parameters. It's, for instance, viscosity, the yield stress value. It's come from rheology. It's characteristic of the material. It depends on kind of lava you have. Most of the time on a volcano, it could be the same kind of lava. On the second kind of data is topography, is the event on the flow rate versus time. At events, there is a flow rate, and we need this flow rate. We need a good topography. It's it's highly sensitive to the topography. For instance, on Hawaii, Kilauea, we have programmed with topography because before the flow, the lava flow, there is trees. So there is something like 10 meters of trees. And with LIDAR data, for instance, we get the topography on the top of the trees. And if we consider the after the flow rate, there is no more trees, and so there is a less high topography. With but there is instead a higher level of lava. There is 2 or 3 meters of lava, so we don't know what was the real topography before the flow. And for the simulation, for the computation, we need the topography before the flow and without trees. So it's not obvious, it's kind of cooking to delete trees on topographies, but it's not very accurate. So there is perhaps no general solution. I don't know, it's not my matter. I am a mathematician. I'm not able to produce topographies.
Yes.
So perhaps you have the good answer for this.
Thank you.
Adalbert, you had a question, maybe one more, Andy, and then we let Caroline.
Ok. En fait, moi, je vais poser ma question en français. C'est par rapport à l'utilisation des modèles. Moi, je me dis des modèles qui sont utilisés dans des zones non habitées et des modèles utilisés dans des zones qui sont occupées par des buildings, si ça sera la même chose. Parce que lorsque nous utilisons, par exemple, lava et Voris sur le volcan Nyiragongo, dans une zone qui a été envahie par la lave en 2002, et c'était une zone où les habitations étaient à plage, donc des habitations qui peuvent être détruites facilement par la lave. Là, on trouve que ces modèles répondaient facilement et correctement avec la trajectoire de la coulée de lave. Et maintenant, lorsqu'on a des buildings, vraiment des maisons qui sont bien construites, solides, qui peuvent dévier la lave, est-ce qu'il y a des paramètres qui sont intégrés dans le modèle pour essayer de tenir compte ce genre de paramètres? Je vous remercie.
Okay, thank you for the question. I will quickly translate to the audience. The question was how buildings can be taken into account when we do modelization. Here at Python, we do modelization in the enclosure where there are no buildings. And the question was from Adalbert Murindo, who is the head of the Goma Observatory, what happened with buildings? So we'll first answer in French and then in English. Adalbert, alors ici, en fait, on ne prend pas en compte les buildings parce qu'il faut qu'on ait il faudrait qu'on ait vraiment la topographie avec les bâtiments. Et à cette échelle-là, on ne l'a pas. Mais je pense qu'il faut faire des tests. Il y a déjà des modèles qui essayent comme le modèle qu'a montré Pierre, qui passent à travers des obstacles. Là, c'était des arbres, comme des poteaux qui ne bougent pas, en fait, qui sont inertes. Et donc, il faudrait faire le même genre de modèle avec une topographie beaucoup plus fine pour voir comment la lave elle serait impactée et voir alors comment l'impact de la lave peut être fait à travers des buildings. Mais c'est à tester, justement. J'espère qu'on le fera. I will just answer this. Here in the model we are using, we are not taking into account the buildings. This could be done actually, I think, by changing either the topography or by using model as the one Pierre showed here with an area of obstacle and how this area of obstacle will slow down the lava or not, or where will go the propagation of lava flow. I think this is a matter that personally I haven't looked into details. Maybe other people in the audience have done that and could also answer what will be the effect. But here with Downflow, we haven't tried that yet. Andy, do you want to add something?
We should probably move on. We're quite a bit behind program, and 5 o'clock is rapidly approaching, and Caroline has arrived now. Hi, Caroline.
Hello. Hi. Nice to meet you.
So we're changing direction a bit now. So we're beginning the society aspects of the hazard and risk, which will continue tomorrow morning. I invited Caroline because she's leading an ANR project in the same program as us, Challenge 9, Protection of the European Citizen. And Caroline's a specialist in communication via social media during crises, no matter what their type, whether they're natural, human, weather-related, geological related. She's actually going to give a few examples that are non-geological, but I believe the crossover of the message is eminently usable for us as crisis responders and managers and modelers in geology, indeed volcanology. So I'll hand the screen or the floor over to you, Caroline, for your presentation.
Thank you. So indeed, I will not talk about volcanic crisis. I apologize because I haven't studied this kind of crisis, but I hope my presentation will lead some discussion. Let's see. Okay. Can you see my screen now?
That's great. That's good.
Okay, perfect. So indeed, I am the coordinator of an ANR project, and we are working on the contribution on social media, and more specifically, how citizens' initiative can be integrated into the crisis management processes. So I have tried to give you some illustrations. Then I will talk about social media in crisis management in a general way, and I will conclude focusing on what we are doing in our project. I hope you will find this interesting. So let's see. Quickly, I'd like to talk about several cases, and each case gives a specific attention on how citizens can use social media during a crisis and why it is important now to know that what's happening on social media, because it raises opportunities but also challenges. So the first example is about the 2011 Genoa flood. I worked on this case study while I was working at the European Commission. I have spent 4 years in the Joint Research Center in Italy, and I was leading these projects on ethics and social media. And at some point, I was asked to look at the social media in crisis management. So quickly, what happened during the night of the 4th November, floods touched violently Genoa. I have put some pictures here, and basically social media has been used in several ways to cover and respond to this emergency situation. What's interesting is that it was students who created a Facebook pages, and the Facebook page reached a lot of likes during the night, and these students had the idea to contact the public institutions, saying, look, we have the possibility to communicate with the public. What I haven't said is that there was no mean anymore of communication, no phone, for instance. So the city decided to open the Wi-Fi and to keep the Wi-Fi open for tourists and for the citizens. So this is why at some point the students thought, okay, maybe we can help, we can support the public institution. So rapidly during the night, the Facebook page became the node of communication between citizens, local authority and rescue teams. So what this is about the methodology. Basically, we looked at what the media said about this case. What I have to tell also is that it was not the first time Genoa was touched by the flood. The city has been already touched during in 1976. And this year, Firenze was also touched by a flood, and Genoa at that time was not so well known, let's say. And so it was only the Italian young people who came to, for instance, clean the city after the flood and so on. And the Repubblica in 2011, they talked about this case, and this gave the idea to the students to create the Facebook page. So these are the pictures used by the Repubblica during the second floods in 2011, and what we can see is that before social media, already there was a kind of solidarity between people, and this is something we are really looking at in our project, is to tell social media becomes a new space of care for citizens in order to act during a crisis. But before social media, people were already helping each other on the real life. So these are just some examples of what the people were telling, why they were engaging in this social media page. And here you have some pictures of young people watching the city after the floods. Just to make a summary about what we can learn about from this case. So social media, as I have said, basically has become this node of communication between citizens and local authority. And what we think it's really interesting, it's the way there was a trust, an immediate trust between citizens and local authority during and after the crisis, to work together. And we have a lot of examples today showing that this question of trust is really important when we talk about crisis management and when we talk about engaging with citizens to respond to the crisis. And what I have said before, it's also that social media is a new space, a new public space to organize operations. The second example, it's about the Hurricane Irma. So Hurricane Irma has touched France, but I looked more specifically on Cuba. What happened during this phase is that this event is that a lot of tourists were in Cuba, and basically when the hurricane touched Cuba, they were all put in the same area, and for a short time, for 2 days, nobody has any news from their family, and people just knew that they were parked in the Varadero area in Cuba, which is northwest, but all the means of communication collapsed, so nobody has any news. French authorities were focused on the French island, which were touched before Cuba, and so there was a completely lack of communication between the tourists, their family, and a lot were very upset and worried. So here we looked at 2 groups on Facebook. And in order to understand what happened and how people organized themselves to face this lack of information. Basically, what have done the French families, is that they started a list of hotels, a list of names, and they managed so the map I am presenting here is the map we have done based on the information produced by the French citizens, which family were locked in the Varadero area. So during the whole weekend, basically, people were sharing the data and trying to put a list saying, okay, I know that my family is here and he was in contact with this person. So, and you know, they built this list. So this was more about the type of information shared. Okay, I'm sorry, but I have to do this because I could not see the whole PowerPoint. So they were sharing information, they were observing what was going on, relaying information also. They were asking questions, and there were also information, traveling information, because people had planned to go to Cuba and didn't know if they have to cancel their travels or not, and so on. And they were also the people in charge of the management of the Facebook page. What we find interesting in this case is the kind of counter-example of the Genoa case, because basically there was not a collaboration between social media, between the institutions and the citizens. And on the contrary, the citizens were by themselves and were trying to build the information, to find the information, and to receive news from their families. Again, there is a reconfiguration of the space of care between citizens, but here trust were not at all in the center of the communication, and when people were trying to phone the French institution saying, look, do you have information? We can give you information. The public institutions were answering, okay, be careful, this is social media, you just have to be patient, and so far we don't know. So we think that this is a very interesting case because it's completely something different from the Genoa's one. Then I will talk about the flash flooding which touched France in November 2019 in the south of France, and I will talk about a specific case of citizens, the VISOV, which are the Volontaires Internationaux en Soutien Opérationnel Virtuel. It's a French version of the VOST, Virtual Operational Support Teams. These are groups of people, citizens, screening social media during a crisis and supporting institutions to deal with the information published on internet and communicating to citizens. So here it's a screenshot of the VISOV Facebook page during the flooding, and I think what I wanted to show here is the way they are mapping. So we have linked with what has done, I would say, normal citizens. So they are doing kind of same approach. Here they are listed the area welcoming citizens during the floodings, because a lot of citizens had to let their place, and so they were building this map, and while they were putting this map, basically they were receiving comments. So I have put here some comment, and I have to apologize because this should be anonymized. Okay, I don't know what happened, but maybe if it's registered, we will have to find a solution to cover the name. You have several comments. So some of the comments were just about updating the map, saying, okay, here there is an area my city is also welcoming, at the school, for instance, and the VISOV are telling, okay, we are updating the map. You have also some citizens offering to welcome people. So here you have, for instance, okay, if necessary, I can welcome 4 people at my place. And you have also citizens asking directly other citizens about how they are doing, because they are thinking that there is a flood in the area. And here's the main question. What is interesting here, it's how social media may constitute an added value for crisis managers, and how social media are changed actually the way crisis managers are dealing with a crisis. Last example is not at all a natural disaster, it's an urban crisis. And it's more about why we have to be aware of what is at stake when using social media and when we engage with citizens. So it's about riots. Riots taking care after Vancouver Hockey Stanley Cup. And so the hockey final was taking place in Vancouver. Vancouver is losing and riot starts in the city. During this crisis, social media has been used in several ways. Citizens witnessing the event, rioters taking pictures of themselves, local authorities after the crisis, so the days after, asking citizens to publish or to send them the pics they have taken in order to be able to identify rioters. So here is the screenshot of the Vancouver Police Department at the time of the crisis. So you see some pictures and they were asking, do you know these guys? Please let us know. Based on this and based on the call made by the Vancouver Police Department to the citizens to send their pictures, citizens started to create their own Facebook pages. So here you see one of the pages created. Post your photos. And basically what happened is that first citizens start to post a photo, and then they said, oh, but I think I know this guy. So they start to publish the name, and then they start to publish an address. And a lot of people, basically some of the rioters were young people, and some families had to leave Vancouver because citizens started to enforce justice by themselves, publishing this kind of pictures. So then it has been a lot of discussion in the media. The Vancouver Police Department were asking the citizens of stopping this kind of vigilante, and in fact, what it's interesting here is the power of social media and the dangers, the challenges local authorities had also to deal with when engaging with citizens. You have to know what you are doing. You have to know the culture of social media in order to do the best with these tools. So now I'd like to talk quickly about social media and what we are talking about. So social media is a platform 2.0, used to create content, to share the content, to use or consume the content, and to interact with others or with the technical environment. In 2019, Facebook, Twitter, and WhatsApp counted 5.7 billion of users, so it's really powerful tool. And what's interesting in our case is that the nature of social media has changed, and specifically during crisis, because they are becoming more and more collaborative. What are we talking about, and what are the opportunities, the technical opportunities of social media? You have on one side the microblogging activities, and on the other side you have the possibility to crowdsource these activities. So you can collect and share information. You can communicate with others, forwarding information, answering to questions. This is what I have talked about before. On the other side, you can collect instantaneously information, data published on the social media. You can cross the sources and have a more specific picture of what is happening on the ground. And you can also use geolocalization. So we can say that social media offer opportunities like ubiquitous information, instantaneous communication. They are a place where harvesting information, and you have the possibility of crossing the sources. When we look at the crisis management cycle, what I can say is during the state of the art until recently, a lot of research papers were focused on the response and the recovery. More and more now, this crisis management cycle the full one is taken into consideration, and you have more focus and question about the contribution to build a situational awareness about what's happening and to find or to build the actionable information, meaning the information which will support the engagement of means on the ground. On the other side, if we are talking about citizens and about social media as means of communication, it's more about how to communicate to citizens with this tool and how to integrate into the crisis management process their action and initiatives. Okay, so maybe I will, here I had put some chronology about social media during the time, but I think I can pass on this slide. Here I've tried to put some information about the challenges. So from a technical point of view, you have different challenges like the data quality, the question of trust, the content. These are questions we talked about with the crisis managers. You have also question of interoperability, big data, collective data visualization, and recommendation systems. Yeah. On the other side, and this is more my topic, and because I'm work on social science, you have several challenges, legal challenges. This is less true now, but there was until recently an absence of legal basis to involve citizens in the response. We have a new law. It was in July 2020, I think, about the way how to engage citizens in the crisis response when something is happening as collaborators. You have also the question of data protection, of course, because if you are taking all the data published on social media, you have to be really careful about the privacy issues, and I had a lot of cases I could talk about this issue. You have also ethical issues. I talked about trust. It's also a question of accountability, co-responsibility of the stakeholders, and also a question of justice, fairness, because you cannot only focus on social media. You have to reach all the people, and all people are not connected at the moment of a crisis. And finally, you have also some design challenges, which methodology to implement in order to design tools for the crisis managers, for instance. Okay, so let's talk quickly about our project. So as I said, we are working on how to engage with citizens and volunteers through social media during crisis situation. We are working with public institutions like le ministère de l'Intérieur, la zone de défense et de sécurité de Paris, some firefighters department. Here is a big picture of how social media impact practices. So we are working with three types of actors: the professionals, the citizens, and what we call the institutionalized volunteers, like the Visa, for instance. And we are looking at how social media redistribute the action, the practice, the action, and how they constitute a new tool in the panel of all crisis management tools. The first year we worked specifically on how information is created and circulates on social media during a major event. We focused on Wikipedia, on Twitter, and we also looked at the traditional media during crisis. During the second year, we worked on the institutional practices and how to involve the citizens' involvement. We have also in our team les mines d'Albi, which are developing a platform. It's a planification platform, so they use modelization, and they wanted in this project specifically develop a module focusing on citizens. So, as I said, social media, when we are talking about the crisis, what's happening is that social media and citizens are impacting the practice of the crisis managers. How can I say, horizontally, and so there is destabilization of crisis managers about this. They don't know how to deal with this new way of doing. So we are working with them in order to build some recommendations, to work with them of how to integrate social media in their way of doing and how they can interact. We are also observing how they do. And more specifically, some firefighters department are really up to date with this way of doing. And okay, here I put other examples, and what I wanted to say to conclude maybe is that citizens' initiative on social media can be spontaneous. This was the case of for instance, the Genoa flood. This is the second picture you can see on the screen. This was also the case of the first example. It's a Twitter screenshot of the taken during the Bataclan terrorist attack, when citizens were opening their door to welcome people. So this was completely spontaneous. This was again the expression of solidarity, but they were also putting themselves in danger because some of them were publishing their own address. And so it was a complexification of the crisis management for the authorities. They can be also affiliated. This is the screenshot I have put from the Visov Facebook page. And this solidarity again can be on-site and online. And finally, what we have shown during this 3-year project is that there is really two dimensions in social media: the informational dimension with the data which can be collected in order to have a better understanding of what is happening on the ground, but also an organizational dimension with the actions, the initiatives taking place on this virtual space. And I will finish with a last idea about the fact that what we have seen about trust is that this is a personal hypothesis, but the more you are close to the ground, meaning communal, departmental, somehow, the more you are close to the territory, the more it's easy to engage with citizens, because you know the citizen, you know your citizen. And the more you are going up to the crisis management operational chain, and the more it will be difficult to integrate the citizen as an actor, because at that point, the citizen has to be protected. And I think this is something we are seeing at the moment during the crisis, the COVID-19 crisis. The citizen has to be protected and cannot be an actor at that point. So it's really a lot about how to build this mutual trust between citizens and authorities now. And I have finished. Thanks for your attention.
Thank you very much, Caroline.
I can share my screen if you want.
Yeah, let's return to the audience and see if anyone's got any questions for Caroline. Lots of ideas and lots of thought-provoking ideas there. Any questions? Julie.
Yes, thank you for your talk. I was thinking while you were speaking that the volcanic risk is very specific and very complex because of the multi-hazard component and the multi-scales component. And I wanted to know if you have developed specific things with your social media analysis dedicated to this volcanic risk and how it could be used during a volcanic crisis, including these complexities.
Okay, so you are talking about a tool, right? About using social media, or you are just talking about how to deal with citizens and, sorry, I didn't understand.
Yeah, it could be both aspects, like the type of analysis you could develop to collect data during a volcanic crisis with this complex information, and the way you would deal with projects with volcanic risk.
So this is not a question for me, it's a question for the technical team, because I am, you know, as I said, I'm focusing on social media, but I am working with the crisis managers, observing how they deal with this information and how they organize themselves, because it's a question of reorganization of the team in the crisis management cell in order to integrate. So they are behind the screen, they are looking at the screen, looking at the information. But I don't know if they are. I know that they are doing a lot about flooding, about fire. I don't know if they have done any work on volcanic crisis. This is for the technical, I would say, technical part. About the communication and how to deal with this kind of crisis during as a crisis manager communicating with citizens or taking information from citizens. What could I say? Oh, this is I don't know. It's too, because I've never, you know, I have never worked on this, so I don't know if I can make some comparison, or what I know is that no, I really don't know, because I do not even know about the kinetics of the crisis. If it's so I prefer not telling any making any mistake, because it's sorry. Challenging, Garis.
Nicola, I believe you've had some experience with crowdsourcing on Piton de la Fournaise to try and gather extra data during an effusive crisis. Do you have any comment?
Not really. I will tomorrow speak about Reunion Island, but I'm sure that Julie will have more expertise about crises in terms of relationship with population. I will show something else tomorrow, but no more information. Maybe Julie have some comment to do because she have an idea of the answer she was waiting for.
Julie,
Julie,
you cannot ask question you would answer.
No, I had no preconception about the answer. I was thinking more about the social media. I'm not really used to like Twitter, Facebook, etc. I've never done any analysis about that. But that's true that on La Réunion you have other kinds of media which are more culturally more important than the social media, I guess, to spread informations about the volcano, namely Radio Freedom. But no preconception on the question I was asking.
But I think it's a very interesting topic because of I just put an alert on my internet and then we save some email. I never open my email. I can give you signs. I think it's signs for 1 year. I just add a specific mailing list and I resave close to 5,000 mail just because of the name of Piton de la Fournaise was on social media. 5,000 mail in 1 year.
Benjamin, you have a question.
Thank you. No, it was just to say that, for example, in Ecuador, we use a lot social media because IGPN is doing both volcanic and seismic monitoring. And we have formularies, for example, for ash fallout and to report earthquake intensities. So that can be very, very helpful during crisis. For example, I will be presenting that in the next weeks for the IGPN for Sangay volcano, because every time there is a paroxysm, we send to the community the formulary so they can fill with information about where and when the ash is falling and even give us some information, additional information. That's working pretty well over the last crisis.
Oriel.
But I'm sorry. Do you have any examples of engaging with citizens, not only collecting the data but also engaging? Are you working on this? Because we are really focusing on this aspect.
Yeah, we created a citizen network that is called ROVE. So we have about 150 persons all around Ecuador that have been trained to actually observe ash clouds, fallouts, and report them. So we did this last year in June 2020. And this year we want to make it a little bit bigger, but we have lots of information coming from them and going to them, because that was also the plan. Mm-hmm.
And they can be followed, so they spread the information and the relevant. Yeah. Thanks.
So for that we use WhatsApp. For example, for that we use WhatsApp. Very, very.
Okay, thanks.
Oriel?
Yeah, was maybe Joseph Makundi, if you want to ask your question. I saw you wrote a comment about false alarm. Joseph, do you want to take the word, or should I just? There is this question. Yes, go ahead. About false alarm, and I think this is linked to what you were saying, how to reduce false alarm. Go ahead.
Je peux parler en français?
Pas de problème.
J'ai suivi la présentation. Merci beaucoup et félicitations pour tous les intervenants. Mais là où ça m'a tiqué, ça a attiré mon attention, c'est quand on a parlé des fausses alertes qui sont produites souvent par les touristes. Effectivement, à Goma, nous vivons également la même situation où les touristes partagent des informations sur les situations des volcans ou alors des images sur les volcans, et ces images publiées à l'extérieur produisent des informations sur l'état des volcans qui sont fausses. Pourquoi nous, à notre niveau, nous pensons, après avoir suivi la présentation, qu'il est important qu'on puisse réglementer les expéditions des touristes et des non-chercheurs volcanologues sur les volcans. Et donc, s'ils peuvent être accompagnés par un chercheur, et quand ils trouvent une anomalie, il a le temps de demander, de poser la question, ça c'est quoi, pour trouver une réponse claire par la bouche autorisée qui est le chercheur. De deux, qu'il y a un protocole, si on peut définir un protocole qui lui limite si les informations à partager et les informations à ne pas partager. Voilà un peu ce qui était notre souci par rapport à cette préoccupation. Merci beaucoup.
D'accord. Je ne sais pas si c'était une question. Auriel, vous voulez traduire ou... Non, mais ce que je peux peut-être dire sur... parce que là, on parle de force d'alerte, mais c'est vrai qu'il y a on parle beaucoup de désinformation et de rumeurs en temps de crise, hein, liées à l'incertitude. Et en fait, moi, je dirais qu'il faut déjà faire la différence entre la rumeur et la fausse information ou la désinformation, puisque toute crise a une incertitude et donc va être sujette à une rumeur, alors que la désinformation, c'est vraiment une campagne, hein, c'est vraiment un but il y a vraiment un but de déstabilisation. So what I was saying that it is that during a crisis, you have to be a difference. You have to do to make a difference, between rumors and disinformation. Each crisis has rumors. This is the rules because there is a lot of uncertainty, and so you will have at some point some rumors. Then the question is how to deal with these rumors and how to act the best in order to have minimum of rumors, or if the rumors happen, to close the rumors. Disinformation is more about a kind of political act in order to create this organization. So this is something which is volunteer, I would say. And it's true that related our work, we are not working about disinformation so far. We are now thinking of doing it due to COVID crisis, of course. But with regard to rumors, the work we have done with public institutions, it's about if you occupy the space on social media, if you are present on this virtual public space, the more you will communicate, the more you will be present. When the crisis happens, people know that you are on the social media, you know how to deal with social media, how to communicate, and at this point, you will have less rumors. This is basically the example of Lubrizol, this technological crisis, and when public institutions published and communicate on social media, they were criticized and so on because they were not used to be listened. They did not do it the right way at the right moment and so forth. Du coup, je le reprends en français ou en fait je sais pas, Auriel, sur la rumeur en fait et sur comment agir par rapport à la rumeur sur les réseaux sociaux, sur les médias sociaux. En fait, le travail qu'on fait avec les institutions publiques, c'est vraiment un travail d'acculturation en fait de ces institutions sur comment prendre la parole sur les médias, sur ces médias, et comment communiquer, alerter, prévenir. Et en fait, ça ne se fait pas qu'au moment de la crise, c'est vraiment un travail qui se fait par tout au long de l'année, de manière à ce que lorsque quelque chose arrive, eh bien, déjà les personnes aient l'habitude d'aller voir ou d'écouter sur ces médias l'autorité publique. Et puis pour l'autorité publique, une manière de comprendre et de connaître, de savoir comment on communique sur ces médias. L'exemple, c'est la culture du communiqué de presse qui n'est pas la bonne sur les médias sociaux. On ne communique pas sur les médias sociaux par communiqué de presse. Malheureusement, nous sommes beaucoup dans nos institutions dans une culture du communiqué de presse. Voilà.
Well, we're how long? It's 5:20 by my clock, so we've managed to overrun. Surprise. So at this time of the day in La Réunion, in the real conference, Nicola would now buy us all a beer.
Yeah.
We'd all sit down with the beer and continue filling out the demographics. So please you fill those out this evening over Nicola's beer and submit them so that we can begin to set up the software, initialize the software for the exercise tomorrow. And I'd like to thank all the presenters today and everyone for contributing to a nice discussion and some good points. And we'll begin again tomorrow morning at 9:30 after Auriel's probably made a few more housekeeping announcements.
Yes, okay, same. Thank you everyone, participants and speakers. I want to make just a small announcement. Today we overrun a little bit, but tomorrow we will have less talk and more time for sharing and time for open discussion that I hope will be lively, even if we are at distances. Also, I want to say that on Wednesday, we will have a talk intervention from our colleague from Goma with a translator. So it will be for both languages. So if the title is in French, but we will have an interpret for English and French. And finally, talking about beers, I suggest that for the next days on the evening, everyone can bring a drink, either a coffee or a beer for sharing and have time for discussion. So now either we close or maybe we can leave 10 more minutes for if some people have comments for the day. Andy, what do you think? Should we better close or let a few more minutes? Or if not, we keep all the questions for tomorrow morning, 9:30. We start again.
I think let's keep it for tomorrow morning. Now it's been quite a long and intense and dense day. So I think it's time to have a rest. Have a rest of the day if it's your morning, or a good evening if it's your afternoon. So thank you everyone, and see you all again tomorrow morning. And thank you, Caroline, for
and thank you for inviting me, and I hope we will manage to meet and more discuss. Thanks a lot. Bye bye.
Bye.
See you tomorrow.
Thanks a lot. It was very interesting.
Merci. À demain, on se reconnecte.
Je sais pas s'il y a 2 heures du matin, mais
Ben, tu viens quand tu veux. Ça sera sur YouTube, donc tu pourras voir si tu te réveilles un peu plus tard et poser les questions le soir.
C'était bien que c'est en live, justement, parce que j'ai plein de questions. Comme c'est pas forcément des sujets que je maîtrise, j'ai plein de questions.